Welcome back. I want to conclude the first part of this course by looking at the history of AI. Learning the history of AI and its key contributors provides an essential context for its evolution and interdisciplinary nature. It highlights the ethical challenges faced and acknowledges the pioneers whose work has driven modern advancements. This understanding can guide current and future practitioners in AI development and policy making to responsibly navigate the technology's profound societal impacts. The history of artificial intelligence can be traced back to the mid-20th century when the field was formally established. The first work on neural networks, inspired by the structure and function of the human brain, was based on the idea that we can create intelligent machines by simulating interconnected nodes or neurons like in the human brain. The early work on neural networks started in the mid-1940s with the development of the McCulloch-Pitts neuron and the perceptron, which were simple models of artificial neurons. In 1958, psychologist Frank Rosenblatt introduced the first artificial neural network called the perceptron, which had a single hidden layer. However, neural networks faced numerous challenges during their early development, such as the XOR problem and the limitations of single-layer perceptron, which led to a decline in interest and funding for neural network research. AI research then shifted its focus primarily to symbolic AI, which was perceived to have more immediate applications. The journey of AI has been marked by several milestones, advancements, and challenges. Among the most notable developments during the early years of AI was the emergence of two distinct schools of thought. The first school of thought was mainstream AI focused on reasoning and logic. The second, neural networks, sought to mimic the human brain's structure and function. Mainstream AI, also known as symbolic AI or classical AI, emerged as the dominant approach in the early years of AI research. It was rooted in the idea that intelligence could be achieved by manipulating symbols and using formal logic to represent and manipulate knowledge. Pioneers like Alan Turing, Alan Newell, Herbert A. Simon, Marvin Minsky, and John McCarthy were instrumental in the development of this approach. Early successes in mainstream AI include the development of the General Problem Solver, GPS, and the creation of the programming language Lisp. One of the most famous examples of mainstream AI is the expert system, which uses a knowledge base and a set of inference rules to solve problems in a specific domain. Expert systems were developed in the 1970s and 1980s, and their successes brought significant attention and funding to AI research. The resurgence of neural networks began in the 1980s, when researchers developed new techniques and algorithms to overcome earlier limitations. In 1986, in their seminal paper, Learning Representations by Backpropagating Errors, David Rumelhart, Geoffrey Hinton, and Ronald Williams explicitly applied the principles of Linenma's reverse mode of automatic differentiation to the training of multi-layer perceptrons and demonstrated how this method could effectively adjust the weights in neural networks based on error gradients. There is a little bit of drama in attributing the invention of backpropagation. The Internet usually attributes it to Geoffrey Hinton. However, this was a collaborative effort started by Seppo Linenma for the initial invention of the reverse mode of automatic differentiation in 1970, which is the foundational concept behind what would later be known as backpropagation. However, his work was primarily theoretical and not directly focused on neural networks. Therefore, while Geoffrey Hinton played a crucial role in applying backpropagation to neural networks, this development was the result of collaborative efforts and built on earlier mathematical concepts introduced by Linenma and others. This was a breakthrough in the development of AI. However, this method needed a considerable amount of data and computing power that was not available at that time. Consequently, we had to wait about 20 years for this method to show all its potential. If we look at the revolution of neural networks, everything boils down to this simple architecture that simulates the human brain. Even though our understanding of the neuron has changed in the last decade, its mathematical approximation is still valid today, thinking that a structure like this can learn by simply tuning the weights W is astonishing. In fact, many did not believe it, and in the 1980s, the proponents of artificial neural networks, or ANN, were pushed away almost as amateurs by the scientists working on symbolic models that were basing their research on formal logic. The only evidence that the proponent of ANNs had was to say, "This works because the brain works, so much so that our brain can learn things it was not trained for, like mathematics. Abstract concepts, like mathematics, for which we did not have an evolutionary input to do that, can still be learned using a complex network of neurons." To the proponent of a more symbolic approach, this sounded like a lame excuse, not proof, and the field of ANN languished for many years. There is even a term for this, the AI winter. However, the hunch of the proponents of ANNs was correct. Unfortunately, they could not access enough data and computing power to demonstrate their contribution. With advancements in computational power and the availability of large-scale data, neural networks have evolved into deep learning models, which can learn complex patterns and representations from vast amounts of data. Today, deep learning has become the driving force behind many AI breakthroughs, including image recognition, natural language processing, and reinforcement learning. I will skip the important advancements in computer vision with convolutional neural networks, or CNNs, that predate the advancements of natural language models. CNNs advanced AI in many significant ways and can be considered the first examples of AI outperforming humans in several tasks using deep learning architecture. Regarding natural language processing, the first breakthrough came in 2013 with the introduction of vector space embeddings that use simple neural network architecture to efficiently train a hyperdimensional space of vectors able to capture both semantic and syntactic relationships between words using a continuous space. This was possible through the availability of large corpora of text used to train this model in an unsupervised fashion. This was really outstanding. In fairness, there were earlier attempts at encoding semantic information using continuous vector spaces, like latent semantic analysis or hyperspace analog to language approaches. However, they were either computationally prohibitive, less efficient, or less accurate than Word2Vec. 2017 is the year of another breakthrough in language models, as it allowed for the creation of highly effective and scalable models like GPT, BERT, and T5, which are now the standards in many natural language processing tasks. The paper, "Attention is All You Need," by Ashish Vaswani et al., introduced the transformer model, revolutionizing generative AI by improving how machines understand and generate human language. This model, centralizing on self-attention mechanisms, allows for more effective training of deep learning models, significantly influencing subsequent technologies like OpenAI's GPT series, which excel in generating human-like text across diverse applications. Reflecting on the evolution of generative AI from early neural models to the significant advancements brought by the "Attention is All You Need" paper, we have reached a pivotal moment. The progress showcases the cumulative nature of scientific discovery, highlighting the role of collective effort in driving technological progress. As we move forward, the field is set to continue its growth, offering new opportunities for innovation and societal impact. With a solid foundation, the future of generative AI holds promise for further exploration and application. Next, I will introduce you to the world of generative AI and how to use this technology effectively using prompt engineering techniques. Coming up.